start with chapter 2 on everyday chemistry. This chapter will discuss the air around us and the different ways how air helps us exist on Earth, as well as the types of air pollution and particles that contaminate the air around us. We're going to start by talking a little bit about the concept of parts of a whole, and there's three different ways you can see this expressed in chemistry. One is the idea of a percentage, which is just parts in a whole that is expressed as 100, so something out of 100. And this is probably the most familiar one to everybody. So for example, if I take a square like this and I divide it into 100 little squares, and if I only highlight a certain portion of this, let's say the first two here, then I would say it's 2%. It's 2 out of 100 of these little squares. So for example, here is a design of a living room using this particular graphing paper. In this case, the table to take 2 by 2 area, and that means that's 4%. So that's kind of how you think about using the concept of percentage. Now, there are other ways to do this. You can, for example, have a circle. You divide it by 100 little marks, and then count. If you have like 28 of these degrees, then that corresponds to 28% type A blood, and then there's 20% type B, and so on. This is just another view of that circle, but then now expressing it for air specifically. So the air that we have around us has 80% of it being nitrogen. Oxygen is about 21%, and then there's small quantities of argon and carbon dioxide and other gases. We also have these two other units that expresses parts of a whole, and they're shortened into ppm for parts per million and ppb for parts per billion. So if a percent is parts out of 100, this is parts out of 1,000,000. So in other words, if you imagine that same square, instead of dividing into 100 smaller squares, you're dividing it now into 1,000,000 smaller squares. Why would you want to do that? It's because the quantity that we're talking about is really tiny. Some of these pollutants that contaminate the air around us exist only in 300 parts per million. So it's a much smaller number than a percent. As a result, we have to use these smaller measurements. You can see it actually here for some of the examples. In terms of air alone, hydrogen gas, that's only half ppm, which just means if you imagine dividing this into 1,000,000 squares, the hydrogen gas occupies half of one of those squares. So it's really tiny. So hopefully that would allow you to visualize what's going on. Okay, so we're going to work on a couple of these problems about percentages and calculations using parts per million, so you can see how this is being applied. So the first question is, oxygen makes up approximately 20% of air, and if we have a room that has a total volume of 152 liters, how many liters of oxygen is present? The concept here is just the concept of percentage that we discussed earlier. In this case, our total volume, which is 152, is what 100% is equal to, and then so if we're looking for 20% of that, then it's really just multiplying 20% times 152 liters. And of course, 20% means 20 out of 100. So if you go back to that picture I was showing you earlier on those squares, you're dividing the entire square by 100 little squares, and then you take 20 of that, and you want to know how many liter that 20 of those squares cover. And if you multiply 20% times 152 liter, you get 30.4 liters. So that will be your answer in terms of the volume of oxygen. The second question is sort of similar in nature, but using the parts per million measurement instead of percentage. So here it says the US EPA sets an acceptable concentration of ozone to be 0.070 ppm. And then the air above Santa Monica covers a volume of approximately 4.95 times 10 to the 12 cubic feet. So that's the total air. What's an acceptable volume of ozone that could exist in the air above Santa Monica? Now, it says find appropriate conversion factors. If you need to, you can do that. I don't think you need to in this particular case. The way you want to think about this is pretty much the same as the previous problem. The only difference is that earlier we had it expressed as a percentage in terms of parts of over a whole. Now we have it as parts per million because it's a much smaller level of contaminants that's allowed. So you only can have that much ozone in your sample. Instead of dividing it into 100 little squares, I'm going to divide it now into 1,000,000 squares. So you can imagine how
the size of those squares is going to be really, really tiny, probably not even visible to your eye. And the ozone level that's allowed, it's 0.07 squares. So it's really, really small, the quantity of ozone that you're allowed to have, because it turns out to be a pretty toxic gas at ground level. We were told that the volume of air above Santa Monica is this much. So that would be your hole. And the ozone quantity is only 0.07. Do the calculation as follow. You will take 0.07 ppm, which is the same as 0.07 out of a million, or 10 to the 6, and then multiply that by 4.95 times 10 to the 12, and the answer you get would be 3.465 times 10 to the 5th. Unit is going to be the same. In this case, it's just cubic feet. That's the amount of ozone that you're allowed to have. That number might look big, but remember that you're covering the entire city of Santa Monica, which is a really large space. Now, I want to point out a little bit about the significant figures here. This number that we're given has 2 sig fig. This number has 3 sig fig. So going back to the rules of significant figures that we learned in the prior chapter, our answer should only have 2 sig fig. And so I'm going to round it to 3.5 times 10 to the 5th cubic feet. Notice how these two calculations are pretty much identical. I just multiply whatever the percentage is times the whole. Here I'm multiplying that ppm by the whole, okay?